as I mentioned,
Okay.
a highly related talk is Sunday morning, so you have to stay over or use Tali's machine. So I'm very happy that Jing Chen will talk about crowdsourced Bayesian auctions.
Thanks. So good morning. Crowdsourced Bayesian auctions. This is joint work with Pablo Azar and Silvio Micheli. So, agenda. First of all, let me tell you what is our motivation for considering crowdsourced Bayesian. And then is our model about this crowdsourced Bayesian. Then after this, what we can do in principle in this model. This is an existential result. And then what we constructively do in this model. Finally, I'm going to put all the comparison with related work at the end. Okay. Now, to talk about our result, it turns out that some tools are very important. And here are them. One is to design mechanisms with a richer strategy space. Well, we have seen this tool again and again in the literature of mechanism design. And here is another example. Another tool is what we propose, a new solution concept, which essentially is depending on neutral knowledge rationality. Okay, we are going to see these tools during our talking about our result. All right, so first of all, motivation. So here the problem we are studying is mechanism design. I can summarize in one sentence what is mechanism design. Here, the designers are trying to leverage the player's knowledge and rationality to obtain some outcome that satisfies some desired property. In our work, the property we care about is to generate good revenue in auctions. I'm going to define what is good when talking about our results. But first of all, let's briefly go through what is an auction. So as you know, in general, an auction has some items on sale, and there are n players participating. The players has valuations. Each valuation is a function mapping from subsets of the goods to, say, integers. For example, the blue player may value the iPhone and the Kindle as $310. Now, an allocation is just a partition of the goods among the players, but some goods are allowed to be unsold. For example, here the blue player gets the Kindle and iPhone, and all the other players get nothing. And an outcome is just an allocation where A0 is an unallocated set of goods, and AI is a set the player I gets, plus the price that each player pays. Now the utility for a player is simply his valuation for the goods he gets minus the price he pays. And the revenue of this auction is the sum of the prices. This is what we care about. Now, talking about the auction, it is typically an incomplete information setting, meaning that the players don't know the valuations of the others. Therefore, here we adopt the Bayesian model, meaning we assume that the players' valuations are drawn from some distribution D. Now, what each part knows? Once the valuations are drawn, each player knows his own valuation. And what designers want is try to come up with some mechanism that gathers this information together to help himself to achieve his goal. He wants to leverage the player's private information. And how can he do that? Well, Marison has told us that for single good auctions, actually you can have a mechanism that generates the optimal mechanism possible. But he has some further assumptions. Say he assumes that the distribution of the players' valuations are independent from each other. But also, he has to assume that actually the designer has to know the distribution D. Otherwise, the designer has no way to calculate what is the price, how to allocate. So this is what we call a centralized Bayesian model, meaning the designer has some centralized information in his mind. He can use this information to help himself to decide how to gather information from the players. This is a centralized version. But one question that we want to think about it is how come the designer has such information? Well, maybe in some cases he can obtain enough information, but you can think about in many cases, in many auctions, designers simply don't know enough about the players. What are a player distribution about a painting on sale or whatever, a house? The designer may have no information about it. Therefore, we may want to come up with a different way to model the information structure in this game. That is, the assumption we adopt here is that the players may know each other better than the designer knows them. Why? Because maybe they are companies competing in the same market for a long time, and they have information, they have a lot of information about each other. So here, what we want to do is to shift the information bundle that the designer has to the player side. So what we are going to assume is that the designer is totally ignorant about the information in this system. What is theta? He doesn't know. What is d? He doesn't know either. All the information sits with the players. So as you can see here, the players knows his valuation and knows the distribution. This is an assumption that is adopted by Bayesian-Nash information, by Bayesian-Nash equilibrium. The designer has to know D to at least verify some strategy profile is an equilibrium. However, typically in the mechanism design literature, you can see many work will assume more. That is, it actually assumes that distribution is common knowledge among the players. That is, common knowledge is I know whatever, I know, you know, I know, whatever it is, infinite hierarchy. And I must say that this assumption is still very strong. Because how to interpret the common knowledge, it is, as I put here, I know that, he knows that, I know that, he knows that, I know that, etc., etc., and up to infinity. Although theoretically we can process this assumption in mathematical formulas, but in real life, how many players you see can adopt this common knowledge, this infinite hierarchy in her mind or in his mind? I find this not very realistic to adopt. Therefore, okay, this is one thing about the Bayesian-Nash equilibrium. But there is actually another thing perhaps that is not quite noticed, is that the Bayesian-Nash also has a hidden assumption about the player's information structure. That is, this Bayesian-Nash assumes that each player knows the conditional distribution given his own valuation. But actually, it assumes not just that. It assumes that each player knows no more than this conditional distribution and no less than it. The players must know precisely the D conditional on his own valuation. Why? Because otherwise, if the player knows more information, he may figure out his Bayesian-Nash equilibrium strategy may not be the best response to what he knows. This is actually an example we have seen in the first talk, the Kramer and MacLean mechanism, where they can extract the full surplus at Bayesian-Nash equilibrium, but it is also crucial that the players has a correct knowledge, correct amount of knowledge. If the players knows more than the conditional distribution, they may want to deviate from the Bayesian-Nash equilibrium. So what happened under this assumption is that actually the players are constrained to have precisely this amount of information. He cannot work harder to obtain more information to help himself. Well, I find this assumption a bit unrealistic, because as you can think about, in an auction, in most time, it is the player's best interest to work hard to obtain as much information as he can about his opponents. However, under this assumption, we're actually tying the player's hands together to stop him from obtaining more information. And this is something that we want to avoid. Therefore, to remove these assumptions, we come up with our crowdsourced Bayesian model. And here is what it is. So still we have this Bayesian information setting, and the players know his true valuations. And as I said before, designer is completely ignorant, has no information about the distribution whatsoever. And there is no common knowledge required about who knows what. Further, we don't impose any assumption about the distribution. Say the player's valuation can be IID, can be independent, and can be correlated, whatever. Well, the last assumption maybe is more important, is that we actually allow each player individually know at least this much, at least D conditioned on his own valuation. Therefore, here in the picture, as you can see, I didn't put this D conditioned on theta I there, I put something else, which is D conditioned on some SI. I'll explain to you later what it is. But this explains, reflects the fact that each player knows at least this much. Now, precisely what we mean. We mean that each player may know an arbitrary refinement about his conditional distribution. So he always knows this conditional distribution, but he can try to work hard and gather as much information as he could and to refine this. So pictorially, our knowledge structure is as follows. So for each player I, there exists some partition of the valuation space. And the partition can be really arbitrary, with only one requirement, is that if two valuation profiles belong to the same set in this partition, then these two profiles have to coincide on this ith component. That means that actually reflects the fact that the player I always knows his own valuation. This is a bit consistent requirement. And now, given theta is drawn from the underlying distribution, this player is informed that this unique set where this theta belongs to. Therefore, his information would be his theta I, and this distribution conditioned on the unique subset of valuations where this theta belongs to. Can be really an arbitrary partition. There is no requirement about the structure except the consistency. As you can see, we don't impose any information requirement on the designers. It is really ignorant. But what does it mean for an ignorant designer? It means that when he designs a mechanism, the mechanism can only take inputs of the player's strategies. See, if the designer is not ignorant, he can have the distribution as an extra input to the mechanism. But here, there is no such input there. Okay? So, this is our model. Looks like the designer is completely ignorant, and the players may have some arbitrary knowledge there. How can we leverage this? Well, our answer is yes, we can, but with proper tools. So, let me tell you, this is our tools that we use. The first is we design mechanisms which has richer strategy spaces. What do we mean by this? Well, consider some classical directly revealing mechanism, where here the strategy space for player I, we denoted by sigma I, is designed to be the player's valuation space, capital theta I. The player has nothing to do but reveal a valuation. But in our direct revealing mechanism, we actually design the player strategy space to be two components. One is his valuation space, and the other is the distribution space of the other player's valuations. So the first one is his knowledge about himself. The second one reflects his knowledge about the others. So this actually, you can interpret it as we are providing a richer knowledge, a richer language for player I to express himself. Now, the second tool, as I mentioned, is a new solution concept, which we call the two-step dominant strategy truthful. Now, you know what is dominant strategy truthful. It is that the player's strategy space is a validation space, and for each player I, no matter what the other players are going to do, player I's best strategy is always to tell the truth. This is his best strategy. Now, what happened to this two-step dominant strategy truthful? Meaning that A, strategy space includes validation and knowledge. B, for each player I, no matter what the other players can do, no matter what his second part action will be, telling the truth about himself is always the best thing he can do, always maximizing his utility, expected utility. And finally, given that all the players are going to tell the truth about themselves in the first part, for each player I, no matter what the second part of the other player's actions will be, player I is always better off by telling the truth about his own true knowledge about the others. So, pictorially, you see each player has two parts, actions, and we don't know what they are. But see, we look at this red player, player I. Well, we still don't know what happened in the other part, but theta I maximized his utility. And further, given that all the other players are telling the truth, no matter what they are going to do, telling the truth about his knowledge is player I's best strategy. So this is a very natural two-step elimination. And actually here, the players only require mutual knowledge rationality, meaning that each player is rational and each player knows that everybody else is rational. There's nothing about common knowledge. Okay, thanks. All right. So we have introduced what is our tools. And now let me tell you our results. The first one is an existence result. Yeah.
Could you go one slide back? The way I should interpret the one slide back?
I couldn't. Sorry.
Okay, so the way I should interpret the delta theta minus I component of the strategy is that this agent is saying I'm type, is announcing I'm type theta I, and my belief is delta of theta minus I. That's the interpretation. And so one condition that you probably need to impose is that given what the other people are doing, and given the beliefs that I declare, I possess, declaring theta I must be a best response. So there must be some consistency between delta theta minus theta I that I'm missing here.
No, actually, we don't need this part. That is that theta I is really the best response, no matter what my belief about the others is. It is dominant. That the belief can be arbitrary. Yeah, we really don't need this consistency. So this is a two-step domination. Okay.
Two-step domination is two iteration.
Oh, by the way, I need somebody to tell me how to go back to the slides.
Backspace or page up? Page up, sorry.
Page. Where? Okay, page up. Okay, thank you. Thank you. What's the problem?
Two-stage elimination of dominant strategies. Then the method you just mentioned.
No, it's something different.
It is different here. Dominant strategy truthful means that there may be some other strategies that is also best response, but the player prefer truthfulness. Okay, so now what we can do in principle? What we care about, as I told you, is revenue in general auctions. So first of all, I'd like to define what is a benchmark that we want to achieve in revenue. This is the benchmark we call the optimal benchmark, which is optimal revenue that a designer can get, use a dominant strategy mechanism under the classical centralized Bayesian assumption. meaning what the designer can do if he knows D. Why I put this hypothetical there? Because remember in our setting, it is crowdsourced Bayesian. The designer is completely ignorant. To him, this benchmark looks great, but he has no way to figure out what it is. It really looks like a pie in the sky. And let me tell you, how can we get this pie? So here is our theorem that for any small integer, for any small number epsilon positive, there exists a two-step DST mechanism under the crowdsourced Bayesian assumption, such that no matter what distribution is, the mechanism will always generate revenue, which is 1 minus 1 over n fraction of the optimum benchmark, minus some epsilon discount, which we don't care. Here, n is the number of players. Now, let me emphasize to you that this result is not asymptotic. This holds for any n greater than or equal to 2. So, if n is very big, 1,100, well, the benchmark looks wonderful. We almost get all the optimum revenue. However, what happened to n equals 2? Well, this means that we get a half of the optimum revenue. Is this bad? Well, actually, let me tell you that this is not bad at all, because we can prove actually this result is tight in some mild technical conditions, even for single good auctions. So this is almost the best we can do, nothing better. So let me give you briefly what is this mechanism. We don't have much time, so I will go pretty quickly. It's very simple. There's a mechanism at the beginning randomly select some player I. This player is a guy chosen to announce his knowledge about the others. So he announced a distribution about the others' valuations. Allegedly, this will be his true knowledge that he has gathered. Now, the other players are all asked to announce their own valuation. And allegedly, this should be the truth. Then what we do? We will run the optimum classical DST mechanism as a black box. You know, this mechanism takes input as a distribution, but now exactly we have the distribution. So we give him the distribution and we give him the valuation profiles for these n-1 players, except player I. And we get an outcome from this mechanism. Notice that here player I is guaranteed to get nothing and will pay nothing. But then we have given to player I some incentive to contribute his knowledge. This is where we use the so-called Breuer's scoring rule to reward player I. I'm not going to tell you the exact formula of this scoring rule, but the only thing you need to know is that this is a function mapping from a distribution and a valuation sum profile here to a real number. And it has a very nice property that take expectation over distribution of v minus I. The expectation is maximized if the valuation is really drawn from this di. So if the di is really a true distribution, this gives the player I incentive to contribute his true knowledge. And finally, there's another nice property that the Breuer scoring rule is always bounded. Therefore, we can shift it, we can rescale it, so that the reward we give to player I is always positive but bounded by epsilon, so that we don't lose much. Now, I'm not going to give you analysis about this mechanism because we are running out of time. But I'd like to make some crucial remarks about it. So first of all, here we are only leveraging one player's knowledge about the others. Because we leverage this player's knowledge, we cannot give him any goods. This is where this 1 minus 1 over n comes. We are losing one player. And second, this mechanism has a black box access to the classical optimum DST mechanism. So, for example, if we have single good auction and distribution are independent, then by plugging in Merson's optimal mechanism, we will get an almost optimal mechanism. But here we are removing the knowledge bundle from the designers to the players. So we work in the crowdsourced Bayesian model.
Players
Sorry?
The first player would be indifferent about his announcement?
No.
How do you say?
No, actually, the Bayes scoring rule has a nice property that it is strictly maximized as a truth. So any line will strictly reduce the reward. And let me point out this is an existential result. Why? Because if this classical optimum DST mechanism exists, then we know there exists this. We know how to construct our mechanism. But if there is no explicit construction of the optimal classical DST mechanism, we don't know how to explicitly construct our mechanism either. So what we can explicitly construct? Well, we indeed can construct some mechanism, but in a simpler setting. This is a setting of single good auctions. And in single good auctions, each player's valuation is just a number. Here we talk about finite cases. Therefore, the number we take to be integers from 0 to some big upper bound. Okay, thank you. So again, let me define to you what we want to achieve in this setting. This is a benchmark we call the star benchmark. So before telling you the benchmark, let me tell you what is star. Star is that given any true valuation profile theta, star will be the player with the highest valuation. Tie is broken lexicographically. Now, in one sentence to summarize, the star benchmark we want to achieve is the monopoly price for this star player given the other player's knowledge. Pictorially, so we know the star players, say the designer has the identity of the star player, and he will gather the information from all the other players about their valuation and their knowledge. Then the designer will put all this information together, and he can calculate a conditional distribution about the star player's valuation. Then from this distribution, he will compute the monopoly price that will maximize his expected revenue. So we'll offer this price to the star player, ask him, hey, this is the price, and take it or leave it. And by doing so, he will maximize the product between this price and the probability that the star player accepts this offer. And the star benchmark will take expectation on the theta. Now, what is the result? The result is that for any small number epsilon and delta, there exists an explicitly constructed two-step DST mechanism under the crowdsourced Bayesian assumption, such that for any single good auction, meaning that for any number of players and any upper bound of the valuation, and for any distribution, this mechanism will generate a revenue which is 1 minus delta fraction of the star benchmark, again minus some epsilon discount. So almost 100%, but with a delta loss. Now let me assure you that actually this star benchmark is not invented by us. It has been studied by Ronen. And there actually Ronen proves that this benchmark is at least half of the optimum benchmark we have seen before. Therefore, using his result, a direct corollary is that the revenue of this mechanism will always be almost half of the optimum revenue. Okay. Now, again, due to time issue, I can only give you some remarks about this mechanism. I'm not even giving you the code. So here, instead of only leveraging one player's knowledge, we are leveraging all players' knowledge except the star players. We are really aggregating knowledge. And the second, why we are losing this delta fraction in the revenue? This is because we want to achieve two-step strict dominant strategy truthful instead of just dominant strategy truthful. If you think dominant strategy truthful is good enough, then you can simply change this mechanism very easily to make it work with 100% of this star benchmark. So delta is there only for the strict dominance. And then another thing I want to emphasize, which is very crucial, is that this mechanism is actually not perfect information. Well, we know in the literature there are many mechanisms. Typically, the way it works is that the players publicly reveal the information and the mechanism do some calculation. But here it is very crucial that some information is not available to the players, meaning that the other players must not know the value of theta star. Why? Because otherwise they will have incentive to lie about their knowledge. And once they want to lie, star player want to lie also. And then we will lose the good benchmark. They're not truthful anymore. So this is very crucial. Okay, thank you. Oh, sorry. I mean, thank you for the reminding. And this is the last part. But I promise you I'll finish pretty soon. So here is some comparison about our result with existing related results. So first, what we can say about the first mechanism in the general auctions. Remember there we achieve 1 minus 1 over n of the optimum benchmark. And we know from the literature that Claude and Robert has this result about single good auction where designer is also ignorant. And there, they generate optimal revenue under Bayesian equilibrium. And as a comparison, what we do for, say, for 2-player is half of the optimal revenue under crowdsourced Bayesian. Actually, this is tight, as I said before, this is tight for 2 players, single good auction and when the distribution is independent. And actually, this gap, one is optimal and one is half optimal, actually shows there is a separation between these 2 different models. And another thing what we can say is about second mechanism for single good auctions. Remember there we achieve 1 minus delta fraction of the star benchmark. As I said before, Ronen had studied this the same benchmark, and he achieved this benchmark exactly under the centralized Bayesian assumption. Here, what we do is to remove the assumption about designers, and we work as we achieve 1 minus delta fraction and the crowdsourced Bayesian. So this is 2 different models. And moreover, if the players' distribution are actually IID, then what can we know? What we know? We know from these authors that in prior phrase setting that nobody needs to know the distribution, that they can learn this distribution when the number of players go to infinity. And they can actually almost achieve this optimal benchmark as n goes to infinity. But here what we have is our bound is not asymptotic. It works for any number of players. So we achieve 1 minus delta fraction of the optimal. Why? Because when the distribution is IID, the star benchmark actually is the optimal benchmark. But our assumption is the crowdsourced Bayesian. And to summarize, what we have achieved here is that we want to help the ignorant designer to leverage information from some arbitrarily informed players. To do so, we have the crowdsourced Bayesian setting, and we have this 2-step dominant strategy truthfulness. And with this, our mechanism can successfully leverage whatever information we have. And that's it. Thank you.